Good morning, ladies and gentlemen. This just a quick recording of questions 10 through 14. Now let's take a look at question 10. For question 10, here's a trolley that's being connected by two springs and is displaced along the axis of the spring and released. Now for a mass spring system, the equation that relates the frequency and period to the mass and the springs as follows. The period of the mass spring system is given by 2 pi square root m over k, and the frequency of the spring system is 1 over 2 pi square root m k over m. Okay, now notice that these two are independent of the amplitude. Okay, now the secret to any simple harmonic motion question is very easy. Just find omega. So let's take a look at this graph over here. Using data from 10.2, calculate the frequency of oscillation of the trolley. Now omega is found over here. This is the maximum kinetic energy, half m omega squared x naught squared. And x naught is found over here. So using the data, this is 75 millijoules. And this is 2.4 cm. We can then incorporate this information into the question to find out what is the frequency of oscillation. So over here, mass is 0.590, omega is 2 pi f, which is what we want to find this, and then x is 0.024, so we fill it in. Then we get the frequency is 3.34 Hertz. Now the trolley loses energy so that the maximum Ke is reduced by 40 millijoules. The way this happens is that due to damping, the oscillation's amplitude slowly decreases. But please note that the frequency will remain the same. The reason is because the spring mass system's equation, T equals to 2 pi square root m over k, is constant so long as the mass and the springs remain unchanged. To find the new amplitude, we'll shift the graph down by 40 millijoules or shift the x-axis up by 40 millijoules. So over here, you can see the kinetic energy of the cart. Now, if the kinetic energy of the cart has reduced by 40 millijoules, this is what it looks like. 10, 20, 30, 40 millijoules. Now, you can see that the amplitude of oscillation is around here right now. Okay, because the cart's energy has been reduced. You notice that the shape of the curve does not change because the shape of the curve depends on omega squared, which is a constant. Now, I know this is very difficult to do in an exam. It's not possible to shift the curve down in an exam. So instead, what we will do is that we'll shift the x-axis up instead. 1, 2, 3, 4. Now, we shift the x-axis up by 40 millijoules. And so now we can find the new intersection point, which will give us the new amplitude of oscillation of the cart. And it looks like 1.65 cm. Okay, so the answer is 1.65 cm. Now let's move on to question 11. In question 11, critical damping is when the oscillation returns to equilibrium at the shortest possible time without any oscillation. That means it does not pass through the equilibrium point. Does not pass through the equilibrium position. So C is the answer. Let's look at question 12. Two objects P and Q are given the same initial displacement and are released. The graph shows the variation with time of the displacement x. So you can see that P is subject to light damping. Now Q is also subject to light damping, but it's a little bit more damping than P. So which graph represents the variation with frequency of the amplitudes of A, P, and Q when they are then subjected to driving forces? So the first part here is about damping. And the second part here is about force oscillation and resonance. So we need to find out what is the resonance curve look like when there is damping. So we combine them together combine. Okay, and then when we combine damping, resonance, and force oscillation, the kind of graph that we will get looks like this. You'll see that as the damping increases, the maximum point of the oscillation, the frequency response of the oscillation, the maximum amplitude would start to reduce. Okay, when you increase the damping and the force oscillation, three things happen. The amplitude at all frequencies is reduced, the frequency at which the maximum amplitude occurs is also reduced, and the peak becomes flatter. Okay, so let's take a look back at the graph over here, P and Q. So as we increase the damping, the amplitudes are reduced at every frequency. The frequency at which the peak amplitude occurs is reduced, and the curve becomes flatter. C is the answer. Now let's take a look at question 13. A block of wood of mass m floats in water, and the frequency is given by 1/2 pi 28 over m. So the only variable that it depends on is m. Okay, so what is meant by the term resonance? Now, in order to explain this answer, we will need to cover 3 points. First of all, we must say that there is an external driving force of the same frequency as the natural frequency. Resonance only occurs when there is an external driving force that's subject to force oscillation. Next, when the external driving force is the same frequency, there will be a maximum transfer of energy from the driving force into the oscillating system. Okay, number 2. And then what happens is that the system will have a maximum amplitude. Okay, number 3. So as long as you cover these 3 parts, number 1, that there is an external driving force with the same frequency as the natural frequency of the system. Number 2, there will then be maximum transfer of energy into the system. And number 3, the system will oscillate at maximum amplitude. This is what's called resonance. Calculate the frequency of the water waves is given by the formula F is V over lambda. Next, what is the mass of the block? Now, since the block is in resonance, the frequency of the water waves is the same as the frequency of the block. This must be the same. Okay? So you must state that the water wave frequency and the block frequency is the same. So therefore, substitute this into the equation here of the block. This is the block's frequency. And then you can find m. So this is 3, then find m. So describe what happens if the amplitude of the vertical oscillations of the block are made larger. Now, if water waves of larger amplitude are incident on the block, the energy supply is larger. Okay, now the energy of the water waves is larger, but resonance still occurs. Alright, so the block is still in resonance because the frequency doesn't change. Okay, the frequency is unchanged, frequency unchanged. So with larger energy transferred, the amplitude of the block increases. So here's the logic behind the water having a larger amplitude. Amplitude increase means that the energy of the wave increase, but resonance still occurs, so therefore energy is transferred. Alright, so that means that the block amplitude also increases. Now what about the distance between the crests increasing? If the distance between the crests increases, okay, then the frequency of the water waves decreases. So it's no longer in resonance. So the amplitude of oscillation drops. Okay, now remember that resonance only occurs as a specific frequency. So if the wavelength of the block increases, then frequency decreases. then it's not in resonance, so the block amplitude decreases. Now, it doesn't drop to 0, okay? The amplitude of the block will not drop to 0. So over here, let's say the frequency of the driver is here, so it's resonance over here. But let's say what happens when you decrease the frequency of the driver. If you decrease the frequency of the driver, then the amplitude of the block also falls. You decrease the frequency of the driver even more, the amplitude of the block falls even more. This is no longer in resonance. So resonance only occurs at one specific frequency. Alright? Okay. So let's move on to the next question. What happens if the block absorbs some water? Now, if the block absorbs some water, the mass of the block will increase. If the block absorbs some water, the mass of the block will increase. Now, when the mass of block increase, the natural frequency of the block will decrease. So when the natural frequency of the block will decrease, then resonance is no longer in resonance and the amplitude of oscillation decreases. So here's the logic. Okay, because the frequency of the block is given by 1 over 2 pi square root 28 over m. So if m increases, then the frequency of the block decreases. This is called the natural frequency decreases. And then since the frequency of the driver is the same, it will be not in resonance anymore. When it's not in resonance anymore, the amplitude of the oscillation will decrease. Alright, and now let's take a look at question 14. A driver of constant amplitude and variable frequency causes forced oscillations. Show how the amplitude of the oscillations varies over a wide range of frequencies. Now this is basically copying over from the graph. Okay, so this is y and this is f. So we determine that there is a natural frequency f0. What we'll do is that we will draw a line, okay, and then we will draw a curve that goes up to here and down to here. Now, show the effects of increased damping. What we'll do is that we'll move the peak frequency down and to the left, and then we'll connect up here and down to here. Now, some common errors drawing the curve are as follows. This is what students sometimes do, which is incorrect. Now, they'll draw a backward bending curve like this. Right, this is of course, this is wrong. Please don't do this. Then they'll start here from 0. This is also wrong as well. And then to draw another damping curve, they will draw something like this. You see that over here, it crosses over. This is wrong as well. This is also wrong as well. So these are the various things that students like to do, sometimes do, which is incorrect. Now, the phenomenon illustrated here can cause considerable engineering problems. Explain one such problem and suggest ways that it can be overcome. The phenomenon is known as resonance. One example that is no good is the oscillation of the car body when the rotation of the wheels causes a periodic driving force close to the natural frequency of the car. Alright, so this causes the vehicle to vibrate vigorously, causing damage to the vehicle. One way to overcome it is to fit shock absorbers to the car suspension to increase damping. Now, here's the logic for resonance. First, how to answer the question is as follows. Okay. Now, first of all, we must state the phenomenon, and then we must say that it occurs when the external driving frequency is equal to the natural frequency. And then we'll be specific. And then after that, what it will cause is that it will cause a very large amplitude of oscillation which damages the system. So you can specify what is damaged. Okay, specify what is damaged. Now, next, to solve it, there are two ways to solve it. One is to change the natural frequency of the system. But how do you do it? By adding mass, for example. Okay. Number two is to change the frequency of the external driving force. For example, by changing the rotation speed of the driver, or change the rotation speed of the driver. Okay, driver frequency, driving force. Okay, and the third thing that we can do to prevent destructive oscillation is to increase the damping. Alright, so this would reduces the amplitude, and also it changes the frequency where maximum amplitude occurs. So that it does not coincide with the driving frequency. So because what happens when you add damping is that not only does the amplitude of oscillation drop, but the frequency also becomes mismatched because the frequency will decrease. Now, so long as your answer has all these 4 components, you will get the full marks. Okay, so for example, what happens, we can say that another example will be when a washing machine, okay, is subject to very large amplitude oscillation at some specific rotation speed. Okay, then we say what is a driver? This is due to the unbalanced clothing in the drum when it rotates. Okay, all right, so what will happen, so when the rotation of the drum, okay, when the rotation frequency of the drum matches the natural frequency of the washing machine, okay, resonance occurs, and then the large amplitude of oscillation may damage the washing machine. Okay, so after that, we can say that to solve this problem, the drum should rotate at a frequency, another frequency that is not the same as the natural frequency, right? And this thus the washing machine is no longer in resonance. That's how you will do it. Okay, so change the frequency of the external driver. So you notice that we say resonance occurs, so this will be 1 mark over here. This occurs when the rotation frequency of the drum matches the natural frequency of the washing machine. There will be 2 marks. Then it's subject to a large amplitude of oscillation that causes damage to the washing machine. And then to solve it, rotate at another frequency not the same as the natural frequency. So you can see that all 4 elements are inside this answer. Okay, and that is it for our tutorial. Thank you for listening and have a nice weekend.